Is life an amazing phenomenon exclusive to our planet? Is there life beyond Earth? Humankind has always asked itself this question, but no answer has yet been found. However, thanks to the latest extraordinary advances in astronomy, it appears that we are closer to solving this mystery. State-of-the-art space probes explore planets and moons in our solar system, while sophisticated telescopes scan the universe looking for answers. The results of the research are amazing.
One of the big triumphs of astronomy in the last 2 decades is to show the majority of stars have planets. There are planets all over the place. There are more planets than stars.
These findings have been made possible thanks to the NASA space probe Kepler, whose launch in 2009 marked a milestone in the search for life beyond the boundaries of our solar system. We now know that in our galaxy alone, there are billions of Earth-like exoplanets. Given the vastness of the universe, with more than 100 billion galaxies, it is hard to conceive that somewhere there is no Earth-like planet that can harbor life. Finding it is simply a matter of time.
It's a game changer. It changes what we think about the possibility for life somewhere else. Exoplanets and extremophiles, 2 game changers.
This leads us to think that in apparently harsh environments in our solar system, there is now, or may have been, life. We may find some form of life in the strange methane lakes of Titan, in the oceans hidden under the mysterious icy surface of Europa, in the gigantic geysers of Enceladus, or in the desert plains of Mars.
The second genesis within the same solar system implies that life, the origin of life, is a likely event.
We don't know if the discovery of life will happen first on one of these moons or planets in our solar system, or on an Earth-like exoplanet. But what we do know is that we are closer than ever to unveiling one of the greatest mysteries of nature, whether there is life in outer space. Life, an unbelievably perfect combination of elements able to create living matter. Possibly the biggest mystery of nature. A combination of matter that shows certain attributes that include responsiveness, growth, metabolism, energy transformation, and reproduction.
We don't yet know exactly what life is. We don't have a working definition. Probably my favorite definition is that life is some sort of chemical entity that is self-enclosed and is capable of Darwinian evolution by natural selection.
Some studies state that life may have begun in Earth as early as 4.1 billion years ago. That is still only slightly younger than Earth. A question arises immediately. Is life an exclusive phenomenon of Earth? There's no easy answer to this question. The chemistry of life begun shortly after the Big Bang, 13.8 billion years ago, during a habitable epoch when the universe was only 10 to 17 million years old. life may have emerged independently at many places throughout the universe. Or life may have formed less frequently, then spread maybe by meteoroids or comets between habitable planets in a process called panspermia. In any case, complex organic molecules may have formed in the protoplanetary disk of dust grains surrounding the Sun before the formation of Earth. According to these hypotheses, this process may occur outside Earth on several planets and moons of the solar system, and on planets of other stars, the so-called exoplanets. Since ancient times, humankind asked itself if we are alone in the universe, and if there is life beyond Earth. Those questions may not be easily answered. However, they have always fascinated us.
Astronomers have been interested in the question of life beyond Earth for a very long time. I mean, we can trace back through the ancient Greeks and Romans and Chinese writings speculation about life beyond Earth.
The main issue to search for life in outer space is to establish what are the life support conditions. A source of energy, such as from a nearby star, is needed to drive endothermic or energy-absorbing reactions. Raw materials, predominantly carbon, build and form organic molecules.
So the building blocks of life on Earth, and we know them, there are carbon, hydrogen, oxygen, nitrogen, and others. They are what we are looking on other planets to look for life as we know it.
These building blocks for life, at least as we understand it, are ubiquitous.
Also indispensable is the presence of a liquid or very dense gas as a solvent for biochemical reactions to occur quickly and stably. Liquid water, the life-sustaining universal solvent, at least on Earth, entails certain atmospheric composition and temperatures.
Now, in order to have a habitable environment, you need three things. You need liquid water, and you need organic material, and you need energy. And there are a number of places in the solar system where all three of those things are thought to exist.
Now we already know the key conditions for supporting life. A question arises immediately. How many planets or moons in our solar system meet these conditions? Considering that one of the key prerequisites for extraterrestrial life is the existence of liquid water, there are three candidates in our solar system to have liquid water on its surface. The planet Mars, the Jovian moon, Europa, and the moon of Saturn, Enceladus. Besides Mars, Europa, and Enceladus, which might have liquid water on their surfaces, there is another candidate for supporting life in our solar system, Saturn's largest moon, Titan. Until 2004, Titan remained a great mystery to astronomers, as a dense, opaque haze prevented understanding of its surface. On 2004, the spacecraft Cassini reached Titan and released a small probe named Huygens. That would change everything. These are the images that the Huygens camera recorded as it descended through the haze. Titan's landscape is very similar to Earth's, with mountains, valleys and plains. When the probe touched down on the surface, it revealed something no one expected. There were pebbles everywhere, similar to the rocks of riverbeds on Earth.
When you're looking at those pebbles, yes, they are rounded pebbles and they have been rounded by torrents and rivers. But they are not rocks in a sense that we understand. They are actually water ice, so hard that it behaves like rock.
How were these rocks eroded? Is there liquid water on Titan's surface? At minus 180 degrees Celsius, water should be frozen solid. Cassini's radar had the answer. It showed us that Titan's surface has hundreds of lakes.
The big difference, though, is that they are not made of liquid water. They are made of liquid methane and ethane.
These two hydrocarbons on Earth are volatile gases. But with Titan's chilly temperatures, they are liquid.
The atmosphere of Titan has methane and ethane and other organic materials that provide a very different kind of chemistry, but a kind of chemistry that is reminiscent of what Earth very possibly looked like before life was abundant.
All these worlds are very far away from the heat of the sun, so they are extremely cold, and some of them are exposed to very high levels of radiation, as they have very thin atmospheres. Therefore, their environments are quite hostile to life. However, life might have found its way.
We also now know about extremophiles, forms of life that live in environmental conditions that when I was a student, I was told, impossible. Can't have any life there. It's too hot. It's too cold. It's too acidic. It's too basic. Too much pressure, too much radiation. They have evolved to thrive in those conditions. So this whole new field of study of extremophiles, it's a game changer. It changes what we think about the possibility for life somewhere else.
Extremophiles such as bacteria that live in high temperature, toxic, deep-sea hydrothermal volcanic vents on Earth offer insight into life that could have developed on other planets that mostly share such extreme, inhospitable environments, which also can include freezing temperatures and minimal sun exposure.
This gave us such a different view of actually what was necessary for life to survive. And all of a sudden, the solar system totally exploded. The horizon of what we call habitability and habitable environment completely expanded in ways that we could not have expected at all.
The chances of finding life on any of these remote worlds in the solar system are now much higher. Finding it is simply a matter of time. Of all 160 or so planets and moons in the solar system, Mars has so far received the most interest from astrobiologists. There are many signs that show that very early in its history, Mars was much like Earth, with large areas of liquid water, a thick atmosphere, ample sources of energy for life, and a good inventory of organic molecules.
In fact, what I like to say when I compare the two planets is that you don't have to invent words to describe Mars. You have mountains, you have canyons, you have polar caps, you have dunes.
There is evidence that Mars had a warmer and wetter past. Dried up riverbeds, vast canyons blasted out by epic floods, valleys carved by raging rivers, polar ice caps, volcanoes, and minerals that form in the presence of water have all been found.
There's a lot of evidence for liquid water earlier in the planet's history, much earlier, about 4 billion years ago, and perhaps some transient water in the time since 4 billion years ago.
But the evidence indicates that all that water disappeared from the surface billions of years ago as Mars cooled down and lost its atmosphere. Did life ever get a foothold on the planet?
As we're looking for evidence for ancient life on Mars, some people think that actually we already had some evidence of that life landing on our own planet. And the best example of that is the Allen Hill meteorites.
We had a piece of Mars here in the lab. We still have it. Allen Hills 84001, a rock that was chipped off Mars by an impact millions of years ago, wound around in space, landed on the Earth in the Antarctic ice sheets, and during the 1984 spring collection season, as that ice was melting and those black rocks were picked up in the melt pools, we realized by the gases that are included in that piece of rock that that's a piece of Mars. And we took it apart at microscopic scales. And we had a big scientific controversy because there were scientists that were claiming features in that rock could only have been produced by biology, and other scientists saying, nope, you can get that with geology.
The search for life on the red planet started decades ago. In 1976, a search for microbial life on the red planet was performed for the first time ever. 2 decades later, in 1997, the Pathfinder mission took a new step forward in this search for life adventure. It found magnesium, aluminum, iron, and phosphate in Martian rocks, which are all possible life-supporting materials. In 2008, the Phoenix spacecraft explored Mars' North Pole. After digging a few inches, it found a white material that evaporated several days later. The analysis of that material revealed it was water ice. Satellites scanned both polar caps and found that there was a lot of water ice under a layer of frozen carbon dioxide. If all that ice ever melted, a more than 80 feet deep ocean would cover the whole planet. The same satellites also discovered that there was ice buried everywhere beneath the desert plains. That was a shocking discovery. Mars had huge amounts of water ice everywhere. But could life exist in the buried ice itself? We now know that there are extremophile microorganisms able to live in similar environments in the dry valleys in the Antarctic here on Earth.
Currently, Mars is very dry and very cold. It's like some regions in Antarctica today, and it's kind of like a very cold desert. So liquid water would not be stable. If you opened up a container of water, it would immediately evaporate because it's so dry.
Buried ice was found under a layer of dry dirt, as happens on Mars. At the point where the dirt met the ice, there was a thin film of liquid water where extremophiles thrived, just for a short time. These microorganisms remain frozen and dormant most of the year and they only flourish for a few warm weeks during the summer.
Today, microbes could still live at depth, at some depth, favored by the presence of thin films of water or maybe more liquid water, because the deeper you go, the more the chance that water could be liquid.
During the Martian summer, it's common to reach 20 degrees Celsius at the equator, so the buried ice might melt and create similar conditions to those found in the Antarctic dry valleys.
Any microbes that might have been there, they're probably living within the rocks or under rock coatings. So that's one of the analog sites that my group's been investigating, is microbes that are living underneath the surface, because that might be viable for Mars as well.
A future mission could eventually prove whether this hypothesis is true or not. But there is another possibility, that liquid subsurface water exists on Mars. Mars' huge volcanoes, such as Olympus Mons, could contribute internal heat to sustain subsurface water. This would imply that hydrothermal vents could exist on Mars as well, and therefore it might be also possible that extremophiles, similar to the ones that thrive in the terrestrial hydrothermal vents, might also exist on Mars. However, this is quite unlikely. Everything would change if we were able to find liquid water on the surface. On September 2015, NASA's Mars Reconnaissance Orbiter made an incredible discovery. This spacecraft provided the strongest evidence yet that liquid water flows intermittently on present-day Mars.
It's not a pure transparent water. It's very briny water, very salty water, which allows it to remain stable for a little while at the surface, because the pressure at the surface of Mars is very, very small.
Using an imaging spectrometer, researchers detected signatures of hydrated minerals on slopes where mysterious streaks were seen on the red planet. They darken and appear to flow down steep slopes during warm seasons, and then fade in cooler seasons. This finding proved what anyone could have imagined. On Mars' present-day surface, there is liquid water. Maybe in some of those ephemeral streams of liquid water, microbial life has managed to arise. We will have to wait for future rovers and explorers to confirm this hypothesis. What will really change our understanding of the Red Planet are the NASA and ECA missions, both part of the Mars exploration program. Since 2007, the main goal of space missions to Mars was not just to follow the water, whether in the form of ice or liquid water, but to explore its habitability, and above all, to seek signs of life.
The more we investigate Mars, we obtain more clues that the ancient history of Mars was certainly supportive of life, and then that final step of, did life actually evolve? And then if it did, where did it evolve? And what clues are remaining today, because that was so long ago.
The ultimate aim of missions to Mars is to prepare for human exploration, a step that would really be a new milestone for mankind. The first step in this ambitious exploration program is the ExoMars program, a partnership between ESA and Russia's Federal Space Agency, Roscosmos, with the participation of NASA. Its primary scientific goal will be to search for possible biosignatures on Mars, past or present. ExoMars is a multi-spacecraft program. The first ExoMars mission, ExoMars 2016, is called the Trace Gas Orbiter, TGO. The goal of this orbiter is to study the Martian atmosphere for the presence of methane and other gases. Gases that might be linked to some biological processes. The second mission in the ExoMars program is the 2018 ExoMars rover and landing platform. The ExoMars rover is a rover with a 2 meters core drill to sample various depths beneath the surface where liquid water may be found.
The drill was supposed to penetrate the first couple of meters within the sediments. This way is more probable maybe finding evidence of viable salts.
The third step of this enthralling Mars exploration program is the NASA mission, Mars 2020. The aim of the Mars 2020 rover is to study diverse rocks and soils to understand past habitable conditions on Mars and to seek signs of ancient microbial life. One of its functions is to monitor weather and dust in the Martian atmosphere and test the ability to extract oxygen from the red planet's carbon dioxide atmosphere to prepare for future human exploration. Any of these breakthrough missions might solve the enigma of whether there is past or present evidence of life on Mars. Much further away than Mars, there is another unique world that might harbor life. Our next destination in the search for life is one of the most fascinating Jovian moons, Europa. Europa is one of the 4 largest moons of Jupiter. It's slightly smaller than our moon, and its icy surface is minus 160 degrees Celsius. Virtually everything we know about Europa is thanks to NASA's unmanned space probe Galileo, which passed by Europa 12 times. These were the first images it captured. It is covered by a smooth layer of water ice. In fact, it has the smoothest surface of any known solid object in the solar system.
The surface of Europa is unique in the solar system. It has very few craters, which tells us that the surface is being reprocessed frequently.
Some parts of its surface show blocks of ice that are separated, but seem to fit together like a puzzle. These icebergs could have been shifted by slushy or liquid water beneath.
These cracks probably may extend all the way down to the ocean, to the ocean, or at some point, so you could get some percolation of water.
This peculiar landscape is very similar to sea ice on Earth.
Galileo was able to detect that. All of those things together add up to our picture of how we now know that Europa has a liquid ocean under its surface.
In 1996, the Galileo spacecraft detected a magnetic field on the planet's surface, indicating that there must be some electrical conduction likely to derive from a salty ocean that could be 60 miles deep.
The studies and observations, measurements that have been made in the past decades seems to be converging pretty clearly with the presence of an ocean under the surface of the ice.
So there we have the first key ingredient for life, liquid water. How can water remain liquid at temperatures of minus 160 degrees Celsius? Some sort of mysterious internal heat must be melting the icy crust. Jupiter is the key. Tidal heating from friction due to Europa's eccentric orbit around Jupiter has been proposed.
The ice at the surface of Europa is being cracked. It's not completely sealed. You can see because of gravitational pull and pull, there is this tug of war as Europa is moving around Jupiter. You can imagine that all this friction is creating lots of energy, lots of heat, and then we have good reasons to think that there are hydrothermal system, which means that you have, water being heated by this process.
Volcanoes, deep down, may harbor hydrothermal vents that provide an energy source to heat and maintain liquid water. So we have two of the three conditions for life: a liquid, in this case liquid water, and a source of energy, that interior heat. We would just need some organic compound, and the chances of life arising would skyrocket. The Galileo spacecraft observed that Europa's ice contains carbon dioxide. When this carbon dioxide is strongly impacted by Jupiter's radiation, it can produce simple organic molecules such as formaldehyde that are steps towards life. The aforementioned tides on Europa could also mix life-supporting substances together in the ocean, but nothing has been proven yet. On 2013, NASA reported a surprising discovery on the icy crust of Europa. Some clay-like materials, specifically phyllosilicates, were detected.
Phyllosilicate just means phyllo, like layered silicate, and these are a fancy name for clays. And clays are a kind of mineral that forms in a lot of water. And on Earth, there are some theories that these clays were some of the original minerals that were present when life was evolving.
According to some hypotheses, the presence of these organic associated minerals may have been the result of a collision with an asteroid or comet. With liquid water, an energy source and the necessary chemical building blocks, perhaps delivered by comets or asteroids, Europa opens up the possibility that life could exist in places never imagined. "12,000 feet beneath the Arctic ice sheets, in complete darkness, there are hydrothermal vents that spew out superheated water with lots of toxic chemicals. Scientists think vents like this could also exist on Europa's ocean floors.
We think that the potentially source of energy for an ocean Europa will be the volcanic activity.
We have recently discovered that clustered around the vents, there are extremophile microorganisms that cover miles of the Arctic seafloor. The discovery of life there really raises the possibility of life on Europa.
Probably Europa might be the best candidate for us to find extant life.
The challenge now is to prove that life has been able to thrive in such a bizarre environment. NASA and ESA have planned 2 different missions to Europa that will investigate its habitability in the next few years.
In 2015, NASA approved a new mission to go to Europa and investigate its environment, and particularly to look for habitability.
NASA's Europa Multiple Flyby mission is a spacecraft that will be launched in the 2020s. The spacecraft will be a highly capable, radiation-tolerant probe that will perform repeated close flybys of the icy moon.
We'll also be looking under the surface to learn more about the structure of the ice shell and the structure of the ocean underneath the shell, using radar and magnetic field detectors and other instruments.
The ESA is developing in parallel its own mission, the Jupiter Icy Moon Explorer, the so-called JUICE mission, that is planned for launch in 2022 and arrival at Jupiter in 2030. This spacecraft will spend at least 3 years making detailed observations, not just of Europa, but also of the giant gaseous planet Jupiter and 2 of its largest moons, Ganymede and Callisto. We will have to wait till the next decade to confirm whether or not there is life on Europa. Europa isn't the only intriguing place this far out in the solar system. Could similar conditions exist on other moons orbiting other planets, even further away from the Sun? Orbiting Saturn, there is a small, mysterious moon that is totally different from the rest of its more than 60 moons. This tiny icy moon, only 300 miles across, is Enceladus. In the last few years, this tiny moon has become the main goal for exobiology, as it has revealed some extraordinary conditions for harboring life.
Most of what we know about Enceladus is thanks to a mission called Cassini. It's a mission that it's been going on for many years. It's an orbiter that has been studying the entire Saturn system and its different moons, but it's been paying close attention to Enceladus.
The Cassini mission offered us a close-up of this remote world for the first time ever. These were the first images it took. The surface is white and glittering, and it is carved with fissures, crests, and cracks. At the South Pole, Cassini made a surprising discovery. It photographed some strange, large cracks, seen here in blue. 4 parallel fissures, scientists named the tiger stripes. They are 75 miles long and hundreds of feet deep. They are similar to fault lines on Earth. After several flybys, Cassini's thermal radar revealed something unexpected. The tiger stripes should be colder than the rest of the moon, as they were in the South Pole. However, they were radiating heat. The fissures were at minus 80 degrees Celsius, which was more than 120 degrees Celsius warmer than the rest of the moon.
It's definitely a place where we see evidence that something profound is happening in terms of potential for habitable environment.
But the most shocking finding was still to come. When Cassini was reoriented, it captured a shocking image. Vast jets of ice were erupting into space.
The camera was able to image plumes of water vapor and ice crystals coming off the south pole of Enceladus.
These actual images showed the plumes were ejecting ice particles hundreds of miles out from the tiger stripes.
Those materials are being ejected through fractures on the surface of the moon, which seem to be connecting the surface with the interior.
However, how this small moon can generate so much heat as to be able to maintain such geothermal activity? Scientists believe that Enceladus might have an internal energy source, like Europa. When it orbits the massive Saturn, friction from gravitational process causes it to heat up, melting ice in the moon's interior in the same way as on Europa. These jets were giant geysers of water that erupted from its icy surface, much like those in geological hotspots on Earth.
Cassini actually has a detector that can fly through the plume, pick up some of the particles and analyze them chemically. And when that detector did its work, it found that some of the particles are salty. And the only way to get salt incorporated into a particle is to have it evaporating directly off of liquid. So that was yet another hint that Enceladus has liquid under the surface from which these plumes are emanating.
But could it prove that under the icy crust of Enceladus existed a subsurface ocean like on Europa?
We needed even more evidence. The next piece of evidence was from Cassini flying past Enceladus and just carefully analyzing its trajectory as it flew past Enceladus to directly measure how Enceladus's gravity was pulling on the spacecraft. And when that analysis was done, it found a density anomaly under the entire South Pole, indicating that you have a regional sea of water from which these plumes are emanating.
These jets might be connected to active hydrothermal vents at a subsurface water ocean floor, where the moon's ocean meets the underlying rock, a prime potential habitat for life. But there still wasn't anything that could prove life existed underneath that icy crust. The probe spectrometers detected something really exciting. They found in the jets the basic chemical building blocks of life.
So Enceladus is fascinating because, as far as we can tell, it contains the three basic ingredients for life: liquid water, nutrients, and organics.
But does this strange and alien world actually support life? The geysers could provide easy access for sampling the moon's subsurface ocean. And if there's microbial life in it, ice particles from the sea could contain the evidence astrobiologists need to identify them. There are 2 exploration missions proposed by NASA to Enceladus in the near future that would try to find evidence of life in the tiny icy moon. The first one is the Journey to Enceladus and Titan mission. This is an astrobiology mission concept to assess the habitability potential of Enceladus and Titan, moons of Saturn. The second mission, waiting for approval and financing, is the Life Investigation for Enceladus.
This proposed mission would capture icy particles from Saturn's moon, Enceladus, and return them to Earth, where they could be studied in detail for signs of life, such as biomolecules.
It's relatively simple, technologically speaking, to send an orbiter to Enceladus that can capture those icy particles in the plume and analyze them in situ or bring them back to Earth for detailed analysis in the laboratory.
Unfortunately, none of these missions have been approved yet. So we will still have to wait to unveil whether or not there is life on this tiny, enthralling moon of Saturn. Close to Enceladus, there is the last of the great candidates for life in the solar system, Titan.
Titan is the largest moon of Saturn. It is one of the largest moons in the solar system, and it is also the only moon that is known to have a thick atmosphere.
Data from the Cassini-Huygens mission, which flew by Titan in 2004, demonstrated the existence of hydrocarbon lakes.
Titan is a fascinating world. It's the most alien place in the solar system, so to speak, because it, in fact, other than the Earth, is the only place we know of that has seas of liquid on its surface, but those seas are not made of water.
In these seas and lakes, there are no waves, as the liquid is liquid methane and ethane, which is much less dense than water liquid.
These 2 hydrocarbons on Earth are volatile gases.
But on Titan's minus 180 degrees Celsius temperature, they are liquid. Titan has a very similar landscape to Earth. There are seas, lakes, smoothed rocks on the riverbeds, mountains, valleys, canyons. But these mountains and pebbles are not made by any rock like on the Earth, but they are made of water ice, so frozen due to the minus 180 degrees Celsius temperature on Titan's chilly surface that it behaves like rock.
Cassini's radar images showed that on Titan, liquid methane forms clouds, thunderstorms, and even falls as rain.
Methane in the atmosphere also plays a role similar to water in the atmosphere. On Earth, you have a water cycle. On Titan, methane plays a very similar role. It falls to the surface as rain or mist. We do see channels and rivers where methane is flowing across the surface and doing geological work like we would see water do on the surface of the Earth.
Liquid methane has a cycle very similar to Earth's water cycle. The question is, could it behave like water does on Earth, as a liquid that allows organic molecules to dissolve and interact?
There is no easy answer to this. Titan's atmosphere also contains many organic gases, such as methane, ethane, and hydrocarbons, and possesses conditions that resemble those of early Earth 4 billion years ago that allowed life to develop.
In many ways, the atmosphere of Titan looks like a young Earth in the fridge, much colder, much cooler. But prebiotic chemistry, the same processes are there. What we don't know is whether these prebiotic processes are turning into something that is biological in nature at the surface of Titan or in the subsurface.
However, liquid methane and ethane are much colder than liquid water by some 200 degrees Celsius, and biochemical reactions would occur at painstakingly slow rates. These compounds are also far less capable as solvents compared to water, and therefore much less life-inducing. Water is also missing from the picture due to freezing temperatures of minus 178 degrees Celsius. Several experiments have shown that with an atmosphere similar to that of Titan and the addition of UV radiation, complex molecules and polymer substances like tholins can be generated, substances that could be considered a sort of precursor to life.
What weirdo chemistry, physics, biology could be. People are trying to think in terms of what could be a biology based on methane. That's not the best, apparently, when it comes to provide a structure for biochemistry.
The conclusion is that Titan is a world rich in organic matter, with a methane cycle comparable in atmospheric and geological processes to Earth's water cycle, that is really likely to harbor life. In the last years, NASA and ESA have combined efforts to develop an unmanned space mission that could finally unveil all the Titan's mysteries. But none of them have been approved yet. One of the most exciting missions proposed to unveil the secrets of the methane and ethane lakes of Titan is NASA's Titan submarine. This submarine would explore the depths of the Kraken Mare, the largest known body of liquid on the surface. This mission would be designed to measure the organic constituents on Titan and would have performed the first nautical exploration of an extraterrestrial sea, analyze its nature, and possibly observe its shoreline. As the other proposed mission to Titan, this Titan submarine mission hasn't been given the green light yet.
There's lots of really fun options for exploring Titan, but NASA has not actually selected one of these options.
Therefore, to date, there are no confirmed space missions to Titan in the coming years. But everything could change if a shocking discovery is made in the near future. Whether or not any of these potential space missions finally reveal the existence of life on Mars, Europa, Enceladus, Titan is an unknown. But what we do know is that now we are much closer than ever to finally finding an answer to the question of whether there is life beyond Earth. 50 years ago, the era of robotic exploration of our solar system was just beginning. In July 1965, the Mariner 4 probe sent the first close-up images of Mars. Those blurred images showed that Mars did not have vegetation, much less canals crisscrossing the planet, as envisioned by earlier generations of astronomers. At that time, the most widespread opinion was that Mars was not just the red planet, but also the dead planet, with the chances for life of any kind being considered infinitesimal. Things have radically changed since 1965, thanks to the extraordinary advances of technology that have led us to use more and more sophisticated space probes to explore our neighbors in the solar system. The three vital factors, energy, liquids, and chemical building blocks, are more widespread than has ever been realized. Now it's not so unlikely to find life beyond the Earth in our solar system. We can't deny that such a huge discovery, even if it were just microbial life, would be really shocking for mankind, as it would imply the first step toward believing that we may not be totally alone in the universe. Then, the right conditions could also exist beyond the boundaries of our own solar system, in distant outer space. Life, an unbelievable, perfect combination of elements that is able to create living matter, may be the biggest mystery of nature. Is life an amazing phenomenon exclusive to our planet? In recent years, we have made several amazing discoveries that suggest that the conditions in our solar system for life might be more prevalent than ever imagined. Recent missions are revealing strange worlds, moons that could have vast oceans concealed beneath miles of ice, like Europa, which orbits around the giant Jupiter. Places where jets erupt hundreds of miles into space, like Enceladus, the tiny Saturn's moon. Or moons with a very Earth-like landscape, with mountains, valleys, clouds, and lakes of liquid methane or ethane, like Titan, the largest moon of Saturn. If life was ever possible, or is now a fact in any of those remote worlds in our solar system, with very harsh and different conditions from Earth, that could imply that life could be possible in any other remote world in outer space.
Second genesis within the same solar system implies that life, the origin of life, is a likely event. If it happens twice in the same solar system, it's likely happening everywhere in the universe.
Now, scientists are searching for planets far beyond the boundaries of our solar system, where we might detect life in the near future. Thanks to the NASA Space Telescope, Kepler, launched in 2009, we know that in our galaxy alone, there are billions of Earth-like exoplanets orbiting their stars. Given the vastness of the universe, with more than 100 billion galaxies, it is hard to conceive that somewhere there is no Earth-like planet that can harbor life.
Unless something very unusual happened here on Earth, then life is developed on thousands of millions of planets just in our galaxy, right? If it's not a miracle, then it's all over the place. That's the bottom line.
In recent years, thanks to Kepler, we have confirmed dozens of Earth-like exoplanets that might harbor life, and even intelligent life waiting to be discovered. We don't know if the discovery of life will happen first on one of these moons or planets in our solar system, or on an Earth-like exoplanet. But what we do know is that we are closer than ever to unveiling one of the greatest mysteries of nature, whether there is life in outer space. Is there life beyond Earth? Humankind has always asked itself this question, but no answer has yet been found. It appears that we are closer to solving this mystery. Recent discoveries have uncovered planets beyond our solar system that are believed to be similar in many ways to Earth.
If I got to ride on a spaceship to one planet that we found with Kepler, the one that I would go to is Kepler 186f. It's one of the smallest ones. It's at the right temperature that liquid water could exist on its surface.
Kepler 186f is the first validated Earth-sized planet to orbit a distant star in the habitable zone where liquid water might pool on the planet's surface. The discovery of Kepler 186f confirms that Earth-sized planets exist in the habitable zones of other stars and signals a significant step closer to finding a world similar to Earth. Kepler 186f orbits its star once every 130 days and receives 1/3 the energy that the Earth does from the Sun, placing it near the outer edge of the habitable zone. If you could stand on the surface of Kepler 186f, the brightness of its star at high noon would appear as bright as our Sun is about an hour before sunset on Earth.
Today, when we take a look at what we know about the origins of life on this planet, it leads us to think that the same things that happened here might well have happened elsewhere. And so life beyond this planet is quite plausible in terms of the science that we know today.
We now know there are 4 important candidates in our solar system to harbor life. Mars, Jupiter's moon Europa, and Saturn's moons Titan and Enceladus. On every of them, we can find all of the 3 key ingredients for life: organic compounds, a liquid, and an energy source.
There is water on Mars under the form of ice at the poles and under the surface, but it is also flowing from time to time at the surface during spring and summer.
Although there's no evidence of any form of life on Mars yet, scientists think it might be found soon. On Jupiter's moon Europa, 2 of those key ingredients can also be found.
We do know there is water on Europa. On the surface of Europa, we have an icy crust. This icy crust has been observed using Voyager spacecraft, but also the Galilean spacecraft in the 90s.
Under an eerie water-ice crust, 10 to 30 kilometers thick, that covers this tiny moon, there's supposed to be a liquid ocean, which may be about 100 kilometers deep. The Saturn's moons Titan and Enceladus have become the search for life priority top spots in the recent years.
Titan is the only moon in the solar system that is known to have an atmosphere. It's also the only place in the solar system that has an atmosphere made primarily of nitrogen, except for the Earth. So Titan and Earth are closely linked in that way.
Titan is a fascinating world. It's the most alien place in the solar system, so to speak, because it, in fact, other than the Earth, is the only place we know of that has seas of liquid on its surface, but those seas are not made of water. They're made of liquid methane and liquid ethane.
Titan is the only place in the solar system outside Earth where there are stable bodies of surface liquid. But at minus 180 degrees Celsius, this liquid can't be water. We know there are lakes filled with super-chilled liquid methane and ethane. In recent years, Enceladus, a tiny moon orbiting Saturn, has become one of the main goals for exobiology. Enceladus is a small icy moon, quite similar to Europa, as it has a thick icy crust and an ocean beneath. We know there are vast jets of water ice erupting several miles into space.
Enceladus is one of the most interesting places in the solar system because of the presence of this activity, this geyser-like activity. If we have geyser-like activity, people expect to have water, liquid water.
Recently, in those jets, some of the basic chemical building blocks of life have been detected, so we can be sure that we have on Enceladus the trifecta to harbor life: liquid, organic compounds, and an energy source. But if life was able to emerge in any of those remote and harsh worlds, why couldn't it also arise on any other planet far beyond the boundaries of our solar system?
The second genesis within the same solar system implies that life, the origin of life, is a likely event. If it happens twice in the same solar system, it's likely happening everywhere in the universe.
If we were able to find life within our own solar system on another place, and furthermore, be able to say that it developed, independently, then you're saying within the same stellar system, you had life evolve twice. And the conclusion from that is that life forms very easily.
A generation ago, just the idea of a planet orbiting a distant star was still in the realm of science fiction. So, to think of the possibility of life on a planet like that was simply unimaginable. In fact, the first exoplanets weren't discovered till 1992. That very year, 2 super-Earth exoplanets were found around pulsar PSR 1257+12 at a remote distance of 2,300 light-years away. This announcement shocked the scientific community at that time, as it was the first multi-planet extrasolar system ever discovered. Could any of these super-Earth harbor life? Unfortunately, a pulsar is a very different kind of star from the Sun. In fact, it's a dead star, formed when some of the largest stars in the universe exploded as supernovae.
A pulsar, which is what's left after a star, a really massive star explodes, and you've got this thing which is one step away from being a black hole. While this was really exciting, it was hard to tell what it meant because pulsars are so much different from normal stars.
These may not seem at first to be good places to look for habitable planets. Supernovae are, frankly, quite apocalyptic events that would easily vaporize any ill-fated planets in orbit around the exploding star. that distant world would be bathed in a lethal cocktail of X-rays and charged particles emitted by a star so faint in visible light that it would scarcely cast a shadow on this world's surface. So the chances of life arising in such a weird and hostile environment would be remote. However, the real importance of this discovery was that for the first time ever, the existence of planetary systems beyond the limits of our solar system was confirmed. If we found 2 exoplanets out there, why couldn't there be many more? We had to wait 3 more years to find an exoplanet orbiting a sun-like star, which was far more important because the conditions of such a planet would be potentially similar to any of the planets in the solar system. On October 6, 1995, was the announcement of the discovery of the first planet orbiting a sun-like star in the journal Nature. That star was 51 Pegasi, a sun-like star located 51 light-years away, and the exoplanet was a giant planet.
The first exoplanet found around a star like our own was called 51 Pegasi b. It's very unusual. It's a very large planet. It's bigger than Jupiter. It's more massive than Jupiter. And it's on a very short period orbit. It goes around its star. 1 year on this planet takes 4 days. It's a very short amount of time.
That discovery marked a turning point in the search for exoplanets. From that moment on, many new ones were found. Nevertheless, what radically revolutionized the search for exoplanets was the NASA Space Telescope Kepler.
Before Kepler was launched, there was hundreds of planets that we knew of in systems around other stars, and now we know of thousands. And that's why Kepler was so revolutionary.
The Kepler was a space telescope specifically designed to survey our region of the Milky Way galaxy to discover hundreds of Earth-sized and smaller planets in or near the habitable zone of their respective stars and determine the fraction of the hundreds of billions of stars in our galaxy that might have such planets.
It works very simply. I mean, anybody can understand this. It's just staring at one spot on the sky all the time, never blinks. And it's looking at 150,000 stars. And it just monitors how bright they are, kind of like a camera light meter, really. And occasionally they'll see this star over here, for example. It'll get a little bit dimmer, a very fraction of a percent dimmer for a few hours, and then it'll get bright again. Well, that happens if a planet passes in front of that star.
We've gone from finding 100 planets to over 1,000 planets with Kepler, those that have been confirmed. And there's about 3,000 or 4,000 more which we have strong evidence for, but we wouldn't consider confirmed planets just yet.
Kepler is on the hunt for planets. Kepler has found literally thousands of planets or planetary candidates. It's a planet-finding machine.
In 2011, for the first time ever, Kepler provided scientists with a census of the Milky Way, so we could calculate how many stars in the Milky Way could have a planet like ours. Around 1 billion.
Maybe there are 1 million, maybe there are 1 billion, maybe there are 100 billion planets in the Milky Way galaxy that could support life, the kind of planets that earthly life could survive on. How many of them have cooked up their own life? And we don't know the answer to that, okay? Because that depends on how hard it is to get life started. Just because I give you all these, these worlds doesn't mean that life will get started. But on the other hand, those planets are all made out of the same stuff that Earth is. So again, unless something very unusual happened here and nowhere else, there's going to be biology all over the place.
Just 4 years after its launch, on April 2013, the Kepler team reported one of their first great triumphs, the discovery, for the first time ever, of 2 exoplanets very similar to the Earth, Kepler 62e and Kepler 62f. This discovery created great enthusiasm as it implied the confirmation of Earth-like planets where life might be possible. Each of these planets have a radius 1.6 and 1.4 times of Earth and orbits Kepler-62, an orange dwarf star, in its circumstellar habitable zone. A modeling study also concluded that Kepler-62e and Kepler-62f are likely covered mostly, perhaps completely, in water. Kepler-62e probably has a very cloudy sky and is warm and humid all the way to the polar regions. Kepler-62f would be cooler, but still potentially life-friendly. Unfortunately, they are at a huge distance of 1,200 light-years away in the constellation of Lyra. Thanks to the Kepler mission, we now know that there are tens of billions of planets orbiting stars just in our galaxy, the Milky Way, and we know there are billions of galaxies across the universe. So if in just one planetary system like ours, life arose on one planet, and there are at least 4 more candidates, the likelihood of finding a planet in outer space that could harbor life should be very high. But Kepler has discovered for us not only the existence of Earth-like planets, but also has provided us with amazing data about the universe, such as the confirmation of the existence of planets that orbit around not only 1, but 2 stars, like Kepler-16b. This planet was Kepler's first discovery of a planet that orbits 2 stars, what is known as a circumbinary planet.
So one of the most exciting discoveries from Kepler was that we were actually able to find planets around binary stars. And the first one that was found was Kepler-16b.
Kepler-16b is many people's favorite planet that was discovered with Kepler. It orbits around not 1, but 2 stars at the same time. This was something which was predicted not to exist. 2 stars setting at the same time was just a piece of science fiction. But the universe is stranger than what scientists can imagine, and it turns out that this sort of thing is true.
Since 1992, over 2,000 exoplanets have been discovered. Thanks to future Space Telescope missions planned for launch, the number of observed exoplanets is expected to increase greatly in the coming years. Despite having discovered just a tiny fraction of all of those billions of exoplanets that we think that exist, how could we know how many of them could harbor life? In astronomy and astrobiology, the region around a star where a planet with sufficient atmospheric pressure can maintain liquid water on its surface is known as the circumstellar habitable zone.
The habitable zone is a place, it's kind of a way of thinking about the right way to go look for planets like our own.
The Earth is obviously in the circumstellar habitable zone of our solar system. A potentially habitable planet implies a terrestrial planet with conditions roughly comparable to those of Earth, and thus potentially favorable to life.
There's a sweet spot, an area where it's not too hot and not too cold, and we call that the habitable zone, or some people call that the Goldilocks zone. If you've got a planet in that regime, and if it's small, if it's rocky enough, and it had water, that water would be in a liquid state, more than likely. So that would be a good place to go looking.
On November 2013, astronomers reported, based on Kepler space mission data, that there could be as many as 40 billion Earth-sized planets orbiting in the habitable zones of sun-like stars and red dwarfs just in our galaxy, the Milky Way, 11 billion of which may be orbiting sun-like stars. Those 11 billion exoplanets orbiting stars like our Sun really are a huge number of potential Earth-like worlds. However, Now we know that stars very different from our sun may be a good place to look for life. In May 2016, a team of astronomers announced, for the first time ever, the finding of 3 habitable planets orbiting a star completely different from ours, an ultra-cool dwarf star. It's the first planetary system found around a star like this. The star, named TRAPPIST-1, is just 40 light-years away and is much cooler and redder than the Sun, and barely larger than Jupiter. In fact, stars like this are very common in the Milky Way, and they are very long-lived. The 3 planets are very similar in size to the Earth and might have habitable regions on their surfaces. So the answer to what the best place in the universe is to find life nowadays has radically changed. To date, among all of the more than 1,000 confirmed exoplanets, there are around 50 that are in the circumstellar habitable zone of the star they orbit around. And therefore, they could be potentially considered Earth-like planets, which does not imply these distant worlds may harbor life. However, could life be possible outside those habitable zones? The discovery of hydrocarbon lakes on Saturn's moon, Titan, has begun to call into question the carbon chauvinism that underpins circumstellar habitable zone theory. Liquid water environments have been found to exist in the absence of atmospheric pressure and at temperatures outside the circumstellar habitable zone temperature range.
Just because a planet is outside the habitable zone doesn't mean that it couldn't have life.
For example, Saturn's moon Enceladus and Jupiter's Europa, both outside the habitable zone of our solar system, may hold large volumes of liquid water in subsurface oceans. If we are considering the possibility that life could arise in such harsh environments, which are not in the circumstellar habitable zone, that implies that we should look for exoplanets far beyond those zones. So the chances of finding an exoplanet with conditions to support life are much higher. We know that it's not an easy task to study and analyze the planets and moons of our own solar system, as they are millions of kilometers away from Earth. However, exoplanets are not just millions of kilometers away, but many light years away from Earth. How can astronomers manage to study exoplanets if they are trillions of kilometers away? There are several methods used by astronomers and astrobiologists to discover and to study these extremely distant, mysterious worlds. Before the launching of the Kepler mission in 2009, the most successful technique for detecting exoplanets was the Doppler spectroscopy, also known as the radial velocity method. The radial velocity method relies on the fact that a star does not remain completely stationary when it is orbited by a planet. A planet is much smaller than its star, but it still exerts a tiny gravitational pull or tug on the star as it orbits. When a planet is behind the star, from our point of view, it pulls the star slightly away from us. When it's in front, it pulls the star slightly toward us. This causes the star to wobble back and forth. Astronomers look for this wobbling to find planets. They use something called a spectrograph and powerful telescopes to examine the light coming from a star. A spectrograph, like a prism, splits the light from the star into its component colors, producing a spectrum. Some of the starlight gets absorbed as it passes through the star's atmosphere, and this produces small, dark gaps or lines in the spectrum. As the star moves closer to us, these lines shift toward the blue end of the spectrum. As the star moves away, the lines shift back toward the red end of the spectrum. so the spectrum appears first slightly blue shifted and then slightly red shifted. Therefore, astronomers can look for orbiting planets by looking for these back and forth motions of the lines in a star's spectrum.
And you can work out from the speed that's being pulled towards you and how long it takes to go around in that circle, you can work out the mass of the planet or the companion thing which is pulling it around. If that mass is very small, the thing is a planet. That method has been very successful. It found most of the planets which were discovered early on.
However, the Kepler technique was based on the planet's transit. The transit method is based on the observation of a star's small drop in brightness that occurs when the orbit of one of the star's planets passes. Transits in front of the star. The amount of light lost depends on the sizes of the star and the planet, and the duration of the transit depends on the planet's distance from the star and the star's mass.
With the Kepler Space Telescope, when we look at a star, we don't see the planet directly. All we see is a tiny dip in the brightness of the star when the planet passes in front of it. From the size of the dip, we can work out the relative size of the planet. Is it a big planet or is it a small planet?
The combination of transit photometry and Doppler velocimetry reveals planetary radius, mass, and density, which are some of the main parameters to evaluate the potentiality of the exoplanet as an Earth-like candidate, and so to harbor life.
Once you know the distance away from the star and you know how hot the star is, you can estimate what the temperature on the surface of the planet would be like.
Another of the main parameters to analyze the Earth-like potential of an exoplanet is its atmospheric composition. Atmospheric studies of exoplanets might be performed with spectroscopy during planetary transits. During the transit, the stellar light passes through the atmospheric limb of the planet. Spectral analysis of this filtered light reveals the structure and composition of the atmosphere. Astronomers could identify the most Earth-like exoplanets by detecting the biomarkers, which are the imprints that life forms have on their host planet atmosphere. For instance, the molecular oxygen that we are breathing results from the presence of life on Earth. Unfortunately, with present-day technology, it's extremely hard to closely study the atmospheric composition of those remote planets.
The main thing that's keeping us from being able to do that now, of course, is technology. We don't have the technology, in functioning instruments at the moment to be able to do that effectively. But that's something that will change with other missions in the pipeline, like Jack Webb Space Telescope and other missions that are happening.
Kepler continuously monitors over 100,000 stars similar to our Sun for brightness changes produced by planetary transits. Thanks to this ingenious technique, Kepler has confirmed to date more than 1,000 exoplanets. Scientists think that about a few dozen of them can be labeled as Earth-like. Considering the possibilities of finding an Earth-like exoplanet are much higher in the circumstellar habitable zone of its planetary system, the planet hunting then started to focus on those areas. One of the first discoveries was 70 Virginius B, an exoplanet located approximately 60 light-years away in the constellation of Virgo. 70 Virginius B was located exactly in the middle of the circumstellar habitable zone of its planetary system, so it was supposed not to be too hot or too cold. Unfortunately, further studies reported that this remote world was a gas giant with very high temperatures, which ruled out any potential for liquid water and therefore of life. The early findings were discouraging in terms of detecting an Earth analog. But this was just the beginning. In 1998, a discovery made in the star Gliese 876, a red dwarf located in the constellation of Aquarius at a distance of 15 light-years away from Earth, really encouraged astronomers. a gas giant was detected in its habitable zone, Gliese 876b. Three years later, another gas giant closer to this one was found, Gliese 876c. We know that life as we know it is not possible on gas giant planets such as Jupiter or Saturn. But the big surprise was that both exoplanets may have habitable moons orbiting around them, as Jupiter and Saturn have.
This was one of the first planets to be discovered in the habitable zone, and people theorized that if it had a moon around it, the moon would be rocky, and the moon would be the right temperature to have liquid water.
Why couldn't any of these hypothetical moons around Gliese 876b and c harbor life, as we hope Jupiter's moon Europa or Saturn's moons Titan and Enceladus might?
So it's an exciting place to think about, and maybe an exciting place to look for in the future.
After the discovery of these exoplanets with potential Earth-like moons, several similar exoplanets with moons orbiting around them were discovered. Maybe on any of those remote moons, life arose in the past, or exists in the present, or might appear in the future. After all these early discoveries, we started to approach to the main goal, to find the most Earth-like world. An Earth analog, also referred to as a twin Earth or Earth-like planet, is a planet or moon with environmental conditions similar to those found on the planet Earth. If life could arise on Earth millions of years ago, and if we look for exoplanets similar to our planet, the chances of finding habitable planets skyrocket. Recent discoveries have uncovered planets that are believed to be similar in many ways to Earth, with relatively high Earth similarity indexes. The size is often thought to be a significant factor, as planets of Earth size are thought more likely to be terrestrial in nature and be capable of retaining an Earth-like atmosphere.
From the point of view of Kepler, a planet is Earth-like if it's small enough that it's probably rocky. It's not a gas giant like Jupiter or Saturn.
But size alone is a poor measure, particularly in terms of habitability, because next to us, there is a planet with a very similar size and mass, Venus, where it is almost impossible for life to arise. There are other criteria to be considered, like the surface gravity or the star size and type.
A planet is Earth-like if it's the right distance away from its star that it's in the habitable zone, that it's not too close that it's too hot and all the water that it would have would boil away, and not so cold that if there was any water on it, it would all freeze to ice.
If we are able to examine all of these parameters of an exoplanet, we would be able to know if it is or not a real twin Earth.
So when we say Earth-like for Kepler, we usually just mean that it's small enough that we think that it's solid enough that you could stand on it, but that doesn't mean that it has an atmosphere or that it has an ocean.
It's also often cited that an Earth analog must be terrestrial. That is, it should possess a planetary surface composed of materials similar to Earth's. The conclusion would be that extrasolar planets, or moons, in the center of its circumstellar habitable zone, the so-called Goldilocks position, with substantial atmospheres, may possess oceans and water clouds like those on Earth. In addition to surface water, a true Earth analog would require a mix of oceans or lakes and areas not covered by water.
We believe that water is essential, but just about everything else you can think about, which is important for life, there seems to be life on the Earth that doesn't need it. There is life that survives without sunlight, there's life that survives without oxygen, there's life that survives deep down underneath the ice in Antarctica.
Unfortunately, with the present technology, we can't properly evaluate most of the parameters like the temperature, the atmospheric composition, or the surface of the exoplanets. Nevertheless, considering we have already discovered hundreds of exoplanets, we can't help but wonder if a real Earth analog has already been discovered. On 18th April 2013, astronomers from the Kepler team announced a discovery that created great expectation. For the first time ever, two very Earth-like exoplanets were found. They were the Kepler 62e and the Kepler 62f. And orbits Kepler 62, an orange dwarf star, in its circumstellar habitable zone. They immediately became prime candidates to host alien life. A modeling study also concluded that Kepler 62e and Kepler 62f are likely covered mostly, perhaps completely, in water. Kepler 62e probably has a very cloudy sky and is warm and humid all the way to the polar regions. Kepler 62f would be cooler, but still potentially life-friendly. Unfortunately, they are at a huge distance of 1,200 light-years away in the constellation of Lyra. Soon after, it was discovered an exoplanet even more similar to Earth, Kepler 186f. This finding was a milestone, as it was the first rocky planet found in the habitable zone of its system. It is 492 light-years away from the Earth.
Kepler 186f is possibly my favorite planet to come out of the Kepler mission. It's a small planet. It's maybe 10 to 20% bigger than the Earth. Based on everything we know about planets, it's almost certainly to be rocky. And it's the right distance away from its parent star that, if the atmosphere is right, if the greenhouse effect is right, it could have liquid water on the surface.
After that discovery, several more Earth-like candidates started to arise, like Kepler 438b, Kepler 442b, or Kepler 440b. All of them were very similar to our planet, but none of them was a real twin Earth. But everything changed on July 23, 2015. That day, NASA's Kepler Space Telescope science team shocked the scientific community with an amazing finding. The most Earth-like planet ever was discovered. Its name, Kepler 452b. What made different this one to the other previous Earth analog candidates? Kepler 452b is the very first, apparently rocky planet that orbits a G-type star like our Sun.
It's a planet in the habitable zone around a star which is almost a clone of our own Sun.
After this discovery, the Earth is a little less lonely in the universe. Kepler 452b circles its star, which is about as hot as our Sun, 10% brighter and 20% larger, at an orbital radius just 5% larger than that of the Earth. A year on this planet is 385 Earth days long, just 20 days longer than Earth's.
What makes this slightly less exciting from the point of view as could it be habitable is its size. Our best guess at the size is that it's about 60% bigger than our own Earth.
It is the smallest Earth analog planet ever found in the habitable zone of a G-type star like our Sun. Previous research on super Earth-sized planets like 452b suggests this one has a good chance of being rocky. If it is a rocky world, it weigh in at about 5 Earth masses, giving it a surface gravity of roughly 2 grams, which would mean that our weight would be double on its surface.
Kepler 452b could have a thick, cloudy atmosphere and volcanic activity. Even more exciting than Kepler 452b's Earth-like demeanor is the fact that this world has spent around 6 billion years in the habitable zone of its star. That's considerable time for life to arise somewhere on its surface or in its oceans, should the conditions for life exist. Kepler 452b is about 1.5 billion years older than the Earth. If it was Earth-sized, the planet and its aging, brightening star might be at a point in their evolution where liquid water would be rapidly evaporating from the surface. But because of its higher mass, astronomers believe Kepler 452b could continue to hold liquid water for the next 500 million years or so. So far, it's the only known world in the system, which lies some 1,400 light-years away in the Cygnus constellation. Obviously, we're not going to get there anytime soon, but it's fascinating to imagine that far off in the distant reaches of space, a world very much like our own might already exist. If this twin Earth exists, why couldn't thousands more like it exist? Less than a year after the amazing finding of Kepler 452b, on May 2016, a new discovery shocked the scientific community. Astronomers using telescopes at European Southern Observatory in Chile discovered 3 planets around a dim dwarf star just 40 light-years from Earth in the constellation of Aquarius. These worlds may be the best targets so far found in the hunt for life elsewhere in the universe. They used the TRAPPIST telescope to monitor the brightness of an ultra-cool dwarf star in the constellation of Aquarius, which has been named TRAPPIST-1. TRAPPIST-1 is much cooler and redder than the Sun and barely larger than Jupiter. Stars like this are very common in the Milky Way, and they are very long-lived. This was the first time that planets have been found around one of them. The 3 planets are very similar in size to the Earth and might have habitable regions on their surfaces. But the really exciting result is that these are the first Earth-like planets that are well suited for the detection of life. The ultra-cool dwarf stars are the only places where life could be detected on an Earth-sized exoplanet using our current technology. The light from much brighter star, like the Sun for example, would swamp vital measurements of the atmospheres of any candidate planets. The next step is to make more detailed observations using the next generation of telescopes, such as ESO's, European Extremely Large Telescope, and the James Webb Space Telescope. That will allow astronomers to study the atmospheres of planets like this and to search for molecules related to biological activity, like ozone, methane, or water. Although there is not yet any proof of the existence of life on all of these exoplanets that we've already found, even in the most Earth-like of them, like Kepler 452b, we can't help but wonder if any of those potential forms of life that might have arisen there were or will be able to evolve into intelligent life. If any of those extremely remote worlds was formed billions of years ago, as Earth did, and it became into a habitable planet, then the organic compound had time enough to mix up and organize into living forms. Perhaps any of those living forms might have evolved into complex forms of life, and some of those complex forms of life might evolve into intelligent beings with consciousness. Thanks to Kepler mission research, it's known that just in our galaxy, the Milky Way, there might be millions of Earth analogs, and there are billions of galaxies across the universe.
so the chances are much higher than we could have ever imagined. For that reason, science is carrying out an intense search for intelligent life. The SETI Institute in California is nowadays the main world institution devoted to the search for extraterrestrial intelligence. Its name, SETI, stands for Search for Extraterrestrial Intelligence. This search is based on the use of radio telescopes. Radio telescopes receive radio waves. As we can't go to space aboard spacecrafts to find that intelligent life, what we look for are radio signals.
What we're looking for is a signal that's at one spot on the radio dial. Just like when you're listening to the radio in your car. You know, you tune across the dial, you hear static everywhere, and then at one spot you're near, and there's a station. Okay, that's the signal that's produced by a transmitter somewhere. It's not natural static. It's not like a quasar or a pulsar or galaxies or hot gas, cold gas. All those things in space make radio noise, but it's all over the dial. So we look for signals that are at one spot on the dial, and of course the source of the signal has to be up in the sky. Those are the kinds of criteria we use to know that even if we don't know what it means, we at least know they're there. They're on the air.
Unfortunately, till now, we haven't received a signal that can be really attributed to extraterrestrial intelligence. In the coming years, NASA and ESA, the European Space Agency, have planned to launch several space telescopes that will surely help to unveil the mystery of life beyond the boundaries of our solar system. The most ambitious one is the James Webb Space Telescope. This project is an international collaboration between NASA, ESA, and the Canadian Space Agency, CSA. It will be the premier observatory of the next decade, serving thousands of astronomers worldwide. It will study every phase in the history of our universe, ranging from the first luminous glows after the Big Bang to the formation of solar systems capable of supporting life on planets like Earth, to the evolution of our own solar system. This new telescope, 3 times more powerful than Hubble, will be able to analyze starlight passing through the atmospheres of the closest Earth-like worlds, looking for the telltale signs of life itself, like, for instance, detecting gases in its atmosphere usually linked to life processes such as oxygen, methane, carbon dioxide, or nitrogen.
JWST is really going to help us understand what atmospheres of planets are like under different conditions, and that's going to be a really exciting result.
There is another mission, the CHEOPS mission. CHEOPS comes from characterizing exoplanet satellite. This is an ESA mission dedicated to searching for exoplanetary transits by performing ultra-high precision photometry on bright stars already known to host planets. With all of these new space telescopes programmed to be launched in the coming years, we are sure that finding a habitable exoplanet and any consistent biosignature will be just a matter of time. If we are ever able to find evidence of the existence of any form of life among one of those billions of exoplanets we know are across the observable universe, it would be undoubtedly shocking.
If we did find life somewhere else in the solar system and we were able to do, for example, a genetic analysis to determine that it was distinct from life on Earth, that would be a really earth-shaking discovery.
Living generation might be witness of a finding that would undoubtedly be a turning point in the history of humankind. The discovery of life in outer space.